I'm Kevin Naidoo, and I am a person that works in scientific computing. So what we've done is just by analyzing a set of data, patient data, we came up with a way of identifying a particular cancer type for a variety of different cancers, and breast cancer, colon cancer, lung cancer, and so forth. And that is by just analyzing the gene patterns, a subset of a gene pattern, we can tell whether somebody's got a particular kind of cancer. I'm a glycobiologist or chemical biologist. And so I've been interested in carbohydrate enzymes and mechanisms of processing carbohydrates in various biological systems. And so what I started doing was look at the link between the extent to which an enzyme may be more expressed and the extent to which we could interfere with that process. So I started looking at, if you like, gene expressions of cancers, and we almost stumbled upon this signature, is what one would call it. So cancer is a silent killer. It's unlike other diseases that you would get, which would normally be, the symptoms would be very visible to you. You would get a temperature, or you'd get a swelling or something like that. That's your immune system immediately kicking into play and trying to fight whatever invader that was coming into your body. So if you get a spider bite, for example, you get a swelling, and if you got a bacterial infection, you'd get a temperature and you feel very uncomfortable. The trouble with cancer is that it starts growing in your body because it starts off as one of your normal cells that starts to misbehave, and it misbehaves in different ways. It grows incredibly fast compared to normal cells. It doesn't obey the normal rules. It keeps on multiplying. So, for example, you won't get your liver growing bigger than it should be growing, because there's all kinds of signals that get sent to it from surrounding cells to tell it to stop growing, whereas in the case of tumors, it doesn't do that. So it grows, and not only does it grow, it sends out agents to different parts of your body, and it starts growing all over the place. And that process is called metastasis. So there's it's a very complex being, and some people have in fact compared cancer to an organism, an organ itself, because it's so complicated. It's a set of very complicated cells, and I myself have compared it to almost like a terrorist cell group that sort of invades your body. And within a cell, you won't have only snipers. You'd have a sniper, you'd have a communications person, you'd have somebody that's into, just internet trolling and all sorts of things like that. And similarly, a cancer cell has got all sorts of, each cell has got its own function, and each set of cells do certain things that make it grow so effectively and evade your immune system. So it grows, you don't know it's there until it's too late. On a personal note, I mean, cancer's affected my family personally. I mean, I've lost family members to that. My late wife died of a leiomyosarcoma. Other members of my family have been lost to cancer. So I don't think this is a particularly unusual story, because cancer is an illness that affects 1 in 3 of us. Every 1 in 3 persons on this planet will get cancer. and every 1 in 5 of us will die of it. So, and this outstrips any other disease, anything like HIV or TB or anything like that combined. It's the biggest killer. And so I put a lot of effort and decided, to spend my time using a series of computational tools and data analytics to then focus on this disease, because it's such a huge killer, and it affects so many people, myself included. And so this fight against cancer has been going on for ages, and we've seemed to have made very little progress until recently. And that progress that we're making now is largely due to major innovations in biotechnology, but also innovations in computational technology, our ability to understand large, complicated data sets and all that. Having access to large amounts of data was, first of all, a wonderful thing, which we wouldn't have had a few years ago. It is a challenge, and it remains a challenge to build a large computational piece of machinery when you're in a fairly isolated environment. And by that I mean that we're not in the hub of major cancer institutes, which and those are the people at the various centers in the United States, like the Broad Institute and so forth. And so we had to build quite a lot of the tools ourselves. It's not myself too, it's of my at that time postdoc and now colleague of mine, Johan Shaskani, has done quite a lot of that work. And doing the data analytics, and so that's a big challenge, sort of knowing which techniques to use without seeking help from somebody that might then sort of want to take over the project. That is a challenge, I think, that a lot of South African researchers face, but particularly in a field like this. Where we don't have a large base of expertise, so that's a big challenge. But it's you can turn a challenge into a win as well. If you're in a fairly isolated place, you can it makes you more innovative, I think, because you're under pressure, and so you have to think think your way out of the problem. At the moment, what we're doing is, so what we did was we did all of this analysis on tumor samples from 1,800 patients. And so those are tumor samples. What we really would like to do is get this innovation out and to get it to the point where it's a cheap early diagnostic for cancer. And by that, you would have to analyze blood samples, which is what we're starting to do at the moment. What we would need to do is keep the cost down and keep it sort of below the 3,000 Rand level. And if we can do that, then I think it would be up to patients and people to decide whether they want to be tested for whether they have cancer or not. And this, I think, would be a major advantage and for everyone. The thing about cancer is that if you catch it early, then you can solve the problem. You can solve it just by physically removing a tumor, or giving someone some kind of immuno or chemical therapy very early on. And if you do that and you catch somebody at stage 1, the problem is more or less solved for most cancers. So what this is we hope to position this as an early diagnostic. So you can imagine, if you get to the point, and this is obviously jumping way ahead, if you can get to the point where somebody Any person like yourself or myself, with your regular 1 yearly checkup, you just have a blood test and you see if everything's still okay. And so, like all other kinds of cancers, breast cancer, for example, you would have a physical check to see whether you've got a tumor growing, and that's, things like breast cancer, prostate cancer. Those are good to check physically. But as I said to you before, the problem is that if you're looking for something that you can't see and it's growing somewhere in your body, then those signals are often sent out in the circulating tumor cells that's in your blood. Not really. I'm a basic scientist, and so my drive is always to discover mechanisms and to understand how things work. But at the same time, I always use this little phrase with my students, is that keeping your mind on the application is important, because it keeps you honest and it prevents you from sort of going off and making all sorts of playful discoveries, if you like. I wouldn't do that differently. I think that's that's what we should be doing at universities, is looking at fundamental science with an eye on the potential application. If you keep yourself focused on your basic skill sets, but you keep yourself aware of what's going on around you, this is important, because often the interface between what you're doing and somebody else is doing next door is where the discovery lies. And if you move out of your little silo and just see what people are doing around you, this is where you could possibly make your discoveries. I am curious, right? I'm an intellectual, curious person. I like to analyze the world, and I analyze everything around me, and I use those analytical skills on the things that I do. So, understanding how the world works makes it a less scary place. So understanding how cancer works makes it less scary. I think we are in a great position at being at universities to have the time to understand how things work. And once you understand how things work, you can discover things. And when you discover things, you can invent things. So that chain is something that is available to everyone. But as I said, if you just look around you and see what's going on, and see how you could possibly apply your things to that, then that's great. And that's what makes me get up in the morning, Okay.